spotlighted.
Well, hi, it's a Tuesday night, and I think it was as Rosanna Dana used to say, it's always something. Tonight we've already had one computer crashed hard just before class started, and so I'm pulling my hair out trying to get it up and running. And we're down a person. Bruce is still in Italy for his vacation, so Dave is switching tonight. Hey, thanks, Dave. So anyway, it's going to be some fun tonight. We'll get through it. This is a ham radio class. This is a ham radio upgrade class for those who might already have their general or advanced class licenses and would like to move up to the extra class. We operate out of this book, the American Radio Relay League License Manual for the extra class. This is the 13th edition. This is the book that you want. There are earlier versions of this, but it doesn't have the right question pool, because in the back of the book are all of the questions and all of the answers. So this is the one you want. And we go chapter by chapter. Sometimes we take 2 weeks to go through a chapter. Tonight we're going to go through chapter 5, which is called Components and Building Blocks. And there are 3 sections which could easily be college-level courses for a semester. So we've got 2 hours. So we're going to go through it as best we can with our laser focus on the test questions and the answers. And we also provide reference material for you so you can go further into your studies if you want to learn more about certain topics. So let's go back over to the laptop, please. And here we are, section 5.1, semiconductor devices. Like I said, I mean, this could easily be a field of study, semiconductor devices. And when we're talking about semiconductors, we have to go down to the basic atomic structure. We have to, look at, remember, the nucleus made up of protons and neutrons and electrons spinning in orbits around the nucleus at various levels, energy levels. And most atoms are stable and they have a certain mass number, a certain number of electrons, certain number of protons. Here's the carbon atom, for example. And the outermost shell of an atom is called the valence ring. And so the electrons that are in the outer shell are called the valence electrons. And there is an interesting phenomenon with atomic structure. It's called the octet rule. And it's when atoms are bonded together, the electrons, they occur in pairs, and the pairs often bond together with other atoms to leave 8 electrons in the outermost shell. All right, I haven't shared this in previous classes, so this is something new for you. We're going to have a little musical interlude here. The whole thing is 6 minutes long. I won't play the whole thing, but here is, for your enjoyment, the octet rule.
When I was just a kid, there was a thing I learned in school. I learned it back in chemistry. It's called the octet rule. Octet stands for 8 electrons in an outer shell. And if you aren't following, you soon will know this well. We're talking about bonding and making molecules. And if you're gonna understand, you gotta learn the rules. So learn the octet rule. Learn the octet rule. Learn the octet rule. Learn the octet rule. Boys and girls, it's really kind of cool. Just learn the octet. Now all the electrons, protons, neutrons, you can learn them if you will. The protons and the neutrons, they do form the nucleus. The neutron's charge is neutral and the proton's charge is plus. And negative electrons are in orbit far away. And learning about electrons is a lesson for today. The electrons and the protons, the numbers equal out. If the neutron's not a difference, nothing to worry about. It's all chemical properties and the electrons reside. Remember those electrons, they orbit way outside. They just don't orbit anywhere but in specific shells. The shells might be called energy levels, and you should learn this rule. Learn the octet rule. Learn the octet rule.
Okay, well, we're going to cut it off there because it is 6 minutes long if you want to go through the whole thing. The URL is at the bottom when you get the presentation tomorrow. But know that atoms share electrons in their outer shells in order to get 8 valence electrons. So hold that thought for just a minute. Let's move ahead. So here's a quotation I love. The nice thing about standards is that there are so many of them to choose from. So I'm going to move myself out here, Dave, just for a second. Back when I was studying electronics in high school, which was back in the 70s, believe it or not, it was a great time because it was the transition between vacuum tubes and solid-state devices. And so actually, I had to learn 2 theories of current flow, and so that's what we kind of like to talk about here as far as 2 different standards. There's the electron flow. It's where we talk about current being electrons flowing from the negative polarity. Let me turn on my laser pointer here. We have electrons moving from the negative side of a power source through a load and then back. Vacuum tubes. Electrons flow from a heated cathode through a space up to a positive voltage on a plate. So this is the electron theory of current flow. And so with vacuum tubes, that made a lot of sense, and that's how people taught it. When we started talking about semiconductor devices, however, we then moved over to the conventional flow. The conventional flow notation says that an electric charge moves from the positive on a battery out through a load and back to the negative. So the electron theory corresponds to the flow of electrons taught with vacuum tubes. The conventional theory corresponds to the flow of holes, or the absence of electrons, and that corresponds to solid-state devices. They're really describing the same phenomenon, and you can see it here in this animation. You see the electrons are moving from the right to the left. The little green electrons, they're going from the minus on the battery to the plus, exactly what we said. Whereas holes, or the absence of an electron in a certain atom, is moving from the left to the right. So when you're talking about current flow, always keep that in mind, especially if you're reading an old textbook, because it can get you confused. So that outer ring, that valence ring, has a lot to do with whether a material is a good conductor, like a copper or gold or something like that, or is an insulator, like glass or plastics. And in between is something called a semiconductor. But I'll tell you, pure silicon is not a semiconductor. Pure silicon is actually an insulator. But we'll talk more about how we get to semiconductor status in just a sec. So the most popular kind of semiconductor in use today is silicon. And so here is a silicon atom. Notice it's got 4 electrons in the outer valence ring. And because of the octet rule, when individual silicon atoms come together, then they will try to join themselves up. And when you look at the matrix that is formed, you have then 8 electrons, making that bonding. And when you get a bonding like this, it's very tight, very close together, and you get silicon crystal. So this is a section of silicon. I forgot about this, Dave, but I have your silicon crystal here. Maybe we'll go over to the calculator cam. Dave's wife, Vicki, is into minerals and rocks and whatnot, and they brought this over for us to use. This is, again, silicon crystal. Notice it's so shiny. It's hard. It's very hard. So that's what you're looking for in a crystalline structure that could be made into a semiconductor. But what makes it a semiconductor, because that is an insulator that we just saw, something called dope. So keep that in mind. We'll be talking about that in a second. Some of the earliest radio involved a semiconductor device. Ever play with a crystal radio? Crystal radios were little things you'd build on a breadboard or on some other mounting thing that consisted generally of a capacitor and a coil that you might wind on an oatmeal box, and a galena crystal, also known as lead sulfide, also known as lead glance. And you'd have a wire, a copper wire usually, that would be going down to this galena crystal down here, and you'd have to touch that on the galena crystal at a certain point. Not every point would give you a good radio reception or a signal. You had to touch it, and it was because of impurities. The galena crystal had impurities naturally in it, and when you would find a point where there was the galena crystal, the semiconductor material base, and that impurity, then you would get a diode formed. And that was the basis for the first semiconductor device. Now, later, 75 years ago, I just heard, this is the anniversary, Bell Labs came out with the first transistor, using stuff that doesn't look much different than that crystal radio apparatus that we saw. And their first transistor was made of a semiconductor called germanium. It's still in use, and it was the first semiconductor in practical use, but take a look at it up there. Look at it. It looks just like silicon. It's that crystalline structure that we talked about. So it also bonds in the same way to give that crystal lattice structure. So silicon, as I mentioned before, it's the most popular semiconductor that we use today. It's used in solar panels and power supply diodes and transistors, integrated circuits, etc. It's got 4 atoms in the outer valence ring, as we mentioned before. I've had an interesting career. Dave, come back to me just for a second, if you would. When I graduated from college in 1978, I went to work for the Dow Corning Corporation. Dow Corning was one of the major manufacturers in Midland, Michigan, which was my hometown. I worked in their audio-visual department doing television programs, much like this. One of the offshoots of Dow Corning was something called Hemlock Semiconductor. Hemlock Semiconductor still exists. In fact, it's the largest manufacturer of single and polycrystalline silicon in the United States. Come on back to the laptop. So here's Hemlock Semiconductor. And I got a chance to learn about this and actually make videos about it for the company. So with a single crystal, at the very tip of this here, you have high heat and pressure, and then single crystal silicon forms below it, and these become wafers that can be sliced and used for the building of integrated circuits and other things. And remember I said about dope? Well, it's dope that makes silicon a semiconductor. And you can have 2 different kinds of doped materials. We call them N-type or P-type. When silicon is doped with something like phosphorus, it is called an N-type crystal. It has an excess of electrons. When silicon is doped with a chemical called boron, then it becomes what they call a P-type of material. It has excess holes. So here's an example of N-type material. They're using phosphorus, another thing that can be donated. And so when the lattice is made up, there's always an extra electron that's trying to find a place to go. Or with p-type material, there's an absence of electrons, and there's always a hole that's sitting there. And with this situation, then you have a current carrier capability. You can control current through the materials. But the thing I want you to remember is that p-type material has excess holes, n-type material has excess electrons. And when you dope semiconductor material like silicon with an acceptor donor, acceptor means that you're adding holes to that material and you're creating p-type material. Or if you dope a semiconductor like silicon with donor material that adds electrons, then that's an n-type. And so here's another graphic of adding some doping, and in this case it's indium, added into the silicon matrix, and notice that there's an absence of an electron there. So this would be p-type material. So we looked earlier at that radio that we were trying to hear with the cat's whisker, and we created a diode on the galena material. Diodes are the basic form of semiconductor junctions, and you get this junction by putting p-type material up next to n-type material. So here's p-type material, and here's n-type material. All right, and when you put them right up against each other, there is actually a region in between called the depletion region. Current won't immediately flow through this device until enough electrons or holes build up to force their way through the depletion region. And that's why with silicon diodes, you'll always have a 0.6 or 0.7 volt reading across a good diode, or with germanium diodes, you'll always have a 0.2 volt reading across them. That's because of the junction there, the depletion region. All right, I want to take you back to the 1980s. It's not disco, but it's got a good beat to it. Here. Greenwood, Archer, and Pine, 1982. You dropped a bomb on me, the Gap Band. Anybody remember it? Well, we're not going to talk about the Gap Band. We're going to talk about the band gap. So at the atomic level, it's the energy required for electrons and holes to transition. And that's called the band gap. It has to do with the depletion region. The band gap is a major factor in determining the electrical conductivity of a solid. And substances having large band gaps are generally insulators, and those with small band gaps are called semiconductors and conductors. So the diode's depletion region, I mentioned to you earlier, we have to overcome that in order to get current to flow through a diode. So here we have a silicon diode, and we've got 0.4 volts as a source, and we're trying to go from the positive through here and to the negative, but we haven't overcome the depletion region yet, because remember with the silicon it's 0.6 or 0.7 volts. So there's no current flow. If we do, however, go at 0.7 volts, then all of a sudden current will start to flow through the diode because we've overcome that depletion region. Well, what happens if you reverse the polarity of the power supply? That's down below here, and you can actually cause the depletion region to grow, to get wider. And when I hold my hands up like this, if you remember from the technician class, I'm kind of describing a capacitor. Two plates separated by an insulator. That's a varactor diode, the one on the bottom, the reversed biased diode. We're going to talk more about varactor diodes coming up. So it's the band gap that is one of the causes of the depletion region. It's narrower in germanium, 0.2 volts to overcome. It's wider in silicon, 0.7 volts. And gallium arsenide, which is a relatively new material, it's 1.2 volts to overcome the depletion reading. Now, depletion reading is only one of the ratings or things you need to know about diodes. Power diodes, for example, are rated in peak inverse voltage. That's the amount of voltage they can withstand before they break down in the reverse bias direction. And maximum current, typically 1 amp diodes or 5 amp diodes. If you exceed those, you're probably going to cause the diode to fail due to high operating temperature. That's the #1 cause of diode failure. You'll let the smoke out, so to speak. All right, so this is a power diode. That's what we've been talking about there. That's the first kind of diode. Now, the second kind of diode that's talked about in the book is the Schottky diode. It's very similar, except there is no p-type material, just n-type material. And the p-type material is replaced by a metal wire or material. It's used in power circuits. It has a low voltage drop of 0.2 volts versus 0.7. So a lot of power supplies will use Schottky diodes for that very reason. The galena crystal, well, that's also very much like a point contact diode. This is number 3 of 8 diode types. It's metal in contact with n-type material. If you look at it here, it very much looks like that old cat's whisker. It's low capacitance, and it's used primarily as an RF detector in radios. Most AM radios, conventional radios, use a 1N34 point contact diode as their detector diode. Another type of diode that we need to know about is the hot carrier diode. It's a type of Schottky diode in that there's no p-type material, just n-type material. But instead of a wire, they actually add a metal dot at the junction. And what this does is it gives it low voltage drop and very fast switching. Hot carrier diodes are used for UHF and VHF mixers and detectors. They work well at very, very high frequencies. Regulated power supplies. Regulated power supplies always have to have a reference, and most of the power supplies use Zener diodes or Zener diodes as their reference. They have a specific characteristic when they're reverse biased, is that they'll hold at a constant voltage over a wide range. And so this keeps, if it's a 9-volt Zener diode, this will keep 9 volts at this point, which is a good reference then for a regulated power supply to use to adjust current flow if you want a 9-volt output, or you can make adjustments to it. So Zener diodes are voltage references. And then with that wider depletion region, the varactor diode, also known as a tuning diode, it uses the depletion region capacitance which changes with a bias voltage, and that capacitance then can change a tuned circuit, the resonance of a tuned circuit. Pin diodes, you may have heard about these in radios and linear amplifiers. A lot of linear amplifiers, for example, they have to be switched from receive, so you can receive signals coming in on the antenna, and then when you go into transmit, it has to switch over to transmit. And early linear amplifiers used relays for this purpose. So you'd have transmit receive relays clacking away as you would sometimes send Morse code or be using the push to talk on single sideband. Pin diodes can be used for RF switching. Pin diodes have p-type material, they have n-type material, and they have something called intrinsic or non-doped material right in the middle. And with a pin diode, it's the amount of forward bias that determines the level of RF conduction. And you'll see this is the schematic symbol for a pin diode. They look something like this, and with the intrinsic material in the middle. Now, one thing that pin diodes have to have is low capacitance between one side and the other, because if you had capacitance, well, you'd have RF leakage. So a pin diode, by its nature, has to be designed such that it has low junction capacitance. And here's a block diagram. It's the amount of forward bias going through the diode that will allow RF to pass through or be blocking the RF from going through it. So that can be used for your transmit receive, for example, in a linear amplifier. And finally, the last diode we're going to talk about is the light emitting diode. Pretty much replaced lamps and bulbs as indicators. It emits photons when it's forward biased. You always have to have a current limiting resistor, this guy here, typically about 100 ohms. That keeps the current going through it at a nominal value. If you hook it directly across a power source, it'll blow out. Don't ask me how I know. And of course, LEDs are the things that we use for signage and other things as well. So what's ahead? Well, this is kind of an older presentation because I've actually been seeing some of these materials that we're talking about when we first put this presentation together as future think as being available now to purchase. One of those is gallium arsenide. It's a new type of semiconductor material that works very well at ultra-high radio frequencies and fast electronic switching. They have lower noise, and so it's all in all, it's a very superior kind of material. Now, notice what it looks like. It looks just like the silicon and the germanium that we saw earlier. So this is gallium arsenide. Electrons can travel 6 times faster in gallium arsenide than in silicon. And so they're now starting to make solar cells based on gallium arsenide with much higher output power. Now the rub was that at the time that the presentation was put together, a single wafer of gallium arsenide was $5,000, whereas silicon was only $5. So, you know, but that's coming down. It must, because they're now manufacturing commercially materials using this. And it has to do with something called electron mobility. It's the speed with which electrons move through semiconductors in the presence of an electric field. And gallium arsenide, you can see, is up here. Here's silicon down here and germanium over here. So that's one. Another in the gallium family is gallium nitride. They have 1/10 of the resistance of silicon, so they have very high energy efficiency, faster switching, and they're used in MMICs. We talked about MMICs in the general class. Monolithic microwave ICs. They're little integrated circuits that have standardized impedance values for input and output. They have controlled gain and very low noise. And typically, they don't have a power lead. You power them through an RF choke on the output lead. And you go, well, Gary, I've never seen a MMIC or whatever. Got a cell phone? They're all over inside the cell phones. There are lots of MMICs in there. It's a great engineering tool for designers. Now, what goes along with a MMIC is microstrip construction. It's used in and with MMICs, and it's where you have a conductor of a certain diameter here, or that's not the right word, but width, and it's separated over a ground plane. So this has a constant impedance value, and it allows engineers to get signals in and out of MMICs in a constant impedance without having lumps and bumps, etc. So when we put N-type material and P-type material and another layer of N-type material together, we get bipolar transistors. That's the transistor we saw earlier that was invented about 75 years ago. So here we have a schematic diagram symbol of a bipolar transistor. This is an NPN transistor. I know that because the arrow always points at the N, and so it's emitter, base, collector, NPN. It's a low impedance device. We say that they're current driven, and so a small change in current at the input in this grounded emitter configuration will give a larger change in output collector current. So this transistor could be used for switching and can be used for gain, for amplification. And with a common emitter circuit like we're seeing here, because the emitter lead ultimately is reaching ground through this emitter bias resistor, if we measure the voltage across here, it's just like a diode. An operating bipolar transistor should have a voltage rating there, if it's silicon, of about 0.6 to 0.7 volts. That's a troubleshooting aid. If you know that the transistor is biased for gain to be an amplifier, but you don't have that 0.6 or 0.7 volts there, it's either zero or it's really high, that might be a clue to tell you that transistor's got a problem. when we're talking about transistors, they also have specifications. One of those is gain. And when we're using a common emitter configuration, like we've been looking at before, we use what we call H parameters. H forward common emitter. It's the change in output collector current over the change in base current, the gain in current, the current gain. This is also known as a transistor's beta. Beta and HFE are the same thing. So this is in a common emitter configuration with the input at the base and the output on the collector. Now transistors can be used also in another configuration called common base. And we can't talk then about beta, we have to talk about something called alpha, which is the ratio of the collector current on the output to the emitter current on the input. And the value is usually less than 1 because these are usually used as impedance converters and things like that. But this is known as a transistor's alpha, and that also then designates it's a common base configuration with the base itself going down to ground. Again, how do we design these? How do we make these transistors work? How do we set them up? We don't have the time to go into that tonight because that is what you would study in college, but we just want you to be aware of these situations and some of the terminology. The frequency, the devices can work up to certain frequencies. Well, the frequency at which a common emitter small signal amplifier falls to 0.707 of that at 1 kilohertz, they use 1 kilohertz as a reference, that's called the beta cutoff frequency. So this again is common emitter configuration. Common base configuration, we also have the alpha cutoff frequency, and that's again is the frequency at which current gain falls off to 0.707. So alpha and beta cutoff frequencies are almost always nearly equal, but just be aware of the terminology. So those were bipolar transistors. We just covered them very rapidly. Field effect transistors are another type. We say that these are high impedance devices, and that goes along with it. They're voltage-driven devices. Vacuum tubes are also high impedance voltage-driven devices. They don't have a base collector and emitter. They have a source, gate, and a drain. So here's here's the gate, here's the source, and here's the drain. And this is an N-channel FET because the arrow is pointing at the N material, so this is N-channel. And surface mount device FETs are very common. They're used in low noise UHF preamplifiers or things that you might buy for VHF, UHF weak signal work. And these block preamplifiers typically have a noise figure of 0.5 dB or less. Very, very quiet. So junction field effect transistors, they're voltage controlled. That's the simplest type of FET. They have a gate, a source, and a drain. And they can be P-channel, that's what this is. The arrow is pointing away from the center, or N-channel, see the arrow is pointing at the center. So this is N-channel, this is P-channel. And there's two different kinds. There's the enhancement mode. It's normally off. There's no current flowing between the source and the drain unless you add voltage to the gate. And when you add voltage to the gate, then the field effect transistor will begin to conduct. So that's the enhancement mode. You're enhancing current flow by adding bias. The depletion type operates very much like a vacuum tube. The device is normally on all the time, and you add bias to the gate to valve it off, to turn it off. Vacuum tubes work in much the same way. So that's depletion mode and enhancement mode. And the schematic symbols for the two are here. Here is depletion mode, and here is enhancement mode. You think of the letter E for enhancement, it might, the prongs of the E might fit into the holes there. I don't know how you remember it, but remember the arrow always points to N-type material. And with field effect transistors, one of their weaknesses is they're very sensitive to static. So if you buy FET transistors, they're going to come in a static bag and they're going to have warnings. A lot of MOSFET devices, metal oxide semiconductor field effect transistors, have internal Zener diodes. They're set back to back that they won't conduct unless you go over a certain voltage. And so if there was a spark or a static pulse that comes in here, they will clamp down to ground and prevent the FET from being damaged. So that's internal Zener diodes in MOSFETs. All right, that was a lot. I acknowledge it. But let's answer some questions. Remember our 3-second rule, please. Give it a wait there, and let's see what we've got. So in what application is gallium arsenide used as a semiconductor material?
C. Charlie?
Yes, it is. They're used in very high frequency circuits, microwave circuits. And which of the following semiconductor materials contains excess free electrons?
Alpha.
Alpha.
That's N-type material, correct? And why does a PN junction diode not conduct when reverse biased?
Charlie? No, 1, 2, 3. Sorry.
But you're right. Holes in P-type material and electrons in the N-type material are separated by the applied voltage, widening the depletion region when it's reversed biased. And what is the name given to an impurity atom that adds holes to a semiconductor crystal structure?
Charlie.
Yep, those are called acceptors, indeed. And how does DC input impedance at the gate of a field effect transistor compare with that of a bipolar transistor?
Charlie.
Yes, an FET has higher input impedance. And what is the beta of a bipolar junction transistor?
Delta.
Not delta.
Bravo.
We talked about cutoff frequency, and that may be what you're thinking about, but it is Bravo. The beta, or HFE, is the gain of the transistor. It's the change in collector current with respect to the change in base current in a common emitter configuration. And which of the following indicates that a silicon NPN junction transistor is biased on?
Delta.
You want for a silicon transistor to have a base to emitter voltage of approximately 0.6 to 0.7 volts. And what is the term for the frequency at which the grounded base current gain of a bipolar junction transistor has decreased to 0.7 of the gain at 1 kilohertz? So it's grounded base.
Delta. Delta.
Delta, that's the alpha cutoff frequency. If it was grounded emitter, it would be beta cutoff frequency. And what is a depletion mode field effect transistor?
Bravo.
Not Bravo.
Charlie.
No, not Charlie.
It's alpha.
It is alpha. Yeah, the depletion mode is one that's on all the time until you add bias, and then you can valve it off. You can close it down. That's the depletion mode. All right.
That's weird.
Yeah, I know. There's enhancement mode and depletion mode. It's going to take a while to figure that one out. But okay, in this figure, which is the schematic symbol for an N-channel dual gate MOSFET?
Bravo. Bravo.
So we think it's number 4 in the figures because it's a dual gate. All right, here's gate 1, here's gate 2, that's right. And remember we said the arrow always points to the N material, so this would be N channel. So indeed, it's B, number 4. And which is the schematic symbol for a P channel junction FET?
Alpha.
We see that? Alpha is correct, yep. It's the p-channel material here because the arrow is pointing away from it. Arrow always points at the end material. So what is the purpose of connecting Zener diodes between a MOSFET gate and its source or drain?
Delta.
Static protection, yes. And what is the most useful characteristic of a Zener diode?
Bravo.
Yes, it maintains a constant voltage drop. And which characteristic of a Schottky diode makes it a better choice than the silicon junction diode for use as a power supply rectifier?
Delta.
Yes, it's got 0.2 volts versus 0.7. So if you're starting out with a certain voltage, you're only going to lose a certain amount, a much smaller amount from the diode drop. All right, what property of an LED's semiconductor material determines its forward voltage drop?
Band gap.
Bravo.
That was why we had the song there, the band gap. And what type of semiconductor device is designed for use as a voltage-controlled capacitor?
1,002.
Yeah, thank you. That's the varactor diode, indeed, the tuning diode. And what characteristic of a pin diode makes it useful as an RF switch?
Delta.
It doesn't have a lot of leakage of RF around it because of capacitance. So yeah, the low junction capacitance, it can block RF. That's good. And which of the following is a common use of a Schottky diode?
Delta.
It's a lot to remember, but yeah, this is the one, UHF and VHF mixer or detector. And what causes a junction diode to fail from excessive current?
Blown it up.
Yeah.
Excessive.
Excessive junction temperature, you let the smoke out. Yeah. And which of the following is a Schottky barrier diode?
Alpha.
Right, you've only got N-type material and metal right up against it, no P-type material. And what is a common use for a point contact diode?
RF detector.
That's the 1N34, that little guy, yeah, that's an RF detector. All right, back to some drawings here. And if you're visually impaired, you can always ask your VE team to let them know, and they'll give you a test that does not have any diagrams. All right, so which is the schematic symbol for a Schottky diode?
We all got muted.
Delta.
So you say delta.
Bravo.
It is Bravo, indeed. It's number 6. I forgot to mention to you that it kind of looks like a backwards S, Schottky. So that's a trick you can use. And some of the symbols, when they draw it as an S. So I don't know, but anyway. Whoops, I gave you that one. What is used to control the attenuation of RF signals by a pin diode?
Alpha.
Yes, alpha, forward DC bias. And why is gallium arsenide useful for semiconductor devices operating at UHF and higher frequencies? What characteristic did it have on that graph?
Bravo.
Yep, higher electron mobility. And which of the following materials supports the highest frequency of operation when used in mimics? I heard something, but I couldn't make it out.
Delta?
Delta, yes, indeed, gallium nitride, the gallium family. And which of the most common, which is the most common input and output impedance of mimics? They're used for RF.
Alpha?
Alpha, 50 ohms, indeed. And which of the following noise figure values is typical for a low noise UHF preamplifier?
Alpha?
Yes, 0.5 dB. And what characteristics of mimics make them a popular choice for VHF through microwave?
Delta?
Yep, controlled gain, low noise, constant input and output impedance, 50 ohms, over a specified frequency range. That's mimics. And what type of transmission line is often used for connection to mimics?
Alpha?
Yeah, that's microstrip. That's that line of copper above a ground plane. All right, so how is power supplied to the most common type of mimic?
Early?
Yep, through a resistor or RF choke connected to the amplifier's output lead. And what is microstrip?
Delta?
Precision printed circuit conductors above a ground plane. Constant impedance. Perfect. All right. Section 5.2, Optoelectronics. After we get through this section, we'll take a break. So, light emitting diodes, who knew? They were invented in 1927, I believe, by a Russian. I think you can look in the URLs that I provide you here that give you the story. Something else I didn't know, all diodes emit light. But because they're put in this plastic case or whatnot, you don't see it. Okay, but light-emitting diodes are designed specifically to emit light when they're forward biased. So here's our light-emitting diode, and this is what one actually looks like. You've seen them. They have a positive terminal, the anode, and a negative terminal, the cathode. And when forward biased, they're able to emit photons. So that's a light emitting diode. Note the current limiting resistor, which is always required. It could be either of the leads. We just got to limit current down to a nominal value. This is almost obsolete now, but charge-coupled devices, it's a question on the test. They're used in digital imaging. It samples an analog signal, light, that comes in through a lens, and then the charge-coupled device is read in stages and then passes that information on to another stage to be processed to get a video image. So here's a CCD camera, for example, with a mini lens that could be used for hobby projects and things like that. So charge-coupled devices. I have on my wrist right here a liquid crystal display watch. I can't hold it up. There we go. It is one that turns opaque when voltage is applied. One interesting characteristic of these, though, is they're hard to see if you're wearing sunglasses that are polarized, because if the polarization is not the same as the display here, you can't see anything. I have a problem with my Chevy Avalanche. Some of the displays on its dashboard, if I'm wearing sunglasses, I can't read them because it blocks them. Did you know that monitors, like this monitor back here, they have polarizations as well, as do cameras. So when I was setting up this studio, I had to keep that in mind because there were some cameras that couldn't see this monitor because it was the wrong polarization, horizontal or vertical. So keep that in mind. But that's liquid crystal displays. They also have this characteristic. All right, back in the day, I was introduced to the electric eye. It's a photoresistor, also known as a photocell, whose resistance changes with the illumination level. And it uses a property called photoconductivity. And what this means is more light and the device is more conductive. So one way to think about this is conductivity is the inverse of resistance. Something that's more conductive has a lower resistance. And I was introduced to it at the main entrance of the Montgomery Ward store in Saginaw, Michigan, back when I was a kid, and we'd walk up to the door and get close to it, and all of a sudden the door would open magically. What? and I'd back off and the door would close magically. Well, of course, they had a light source on one side and a conductive cell on the other side, and it was magic to me. It was probably using vacuum tubes as the sensing amplifier in order to control the relays for the door, but that goes back that far. Photoconductive materials back then were probably selenium. Another crystalline semiconductor. They were also used in photo light meters. Anybody remembers those? So here's a look at the selenium crystals, for example. Other optical devices that we need to know about, and these are used today, they're optocouplers, also known as optoisolators. You can find them in dual inline packages like this one right here, and they consist of a light-emitting diode inside the package and a photosensitive transistor. So when the light shines in, then the transistor conducts. But notice there's isolation between the voltages on this side and on this side. It provides electrical isolation. And where this is extremely important is in switching power supplies, where they're actually they're connecting directly to the incoming AC, chopping up that into a high frequency pattern, going through a transformer, a very high frequency transformer, maybe 100 kilohertz or so, and you need to get feedback so that it regulates the voltage, and the feedback is given through this optoisolator right here. But there's electrical isolation between this side and this side, so that people over here are never directly connected to the mains voltage. And this is actually, it was a Polish schematic that I found that kind of illustrated things. So 230 volt, 50 hertz coming in here, and regulated 12 volts on the output there. Solar panels, very popular, and they use the photovoltaic effect, which converts light to electrical energy. Silicon solar cells are still the most commonly available. And solar cell efficiency, here's some definitions. The efficiency of a solar cell is the relative fraction of light that is converted to current. I didn't like this definition, but here's how I understand it. You've got a bright day and you've got 100% of light coming down on the solar cell, and you'd think that it would convert 100% of the light. That would be 100% efficient. Great. But if you get dirt or other things that block some of that, or shade or whatever else, then the solar cell might only be able to use 50% of that, and that would degrade its efficiency. That's how I understand it. Now, solar cells, individual solar cells, put out 0.5 volts DC. And in the big solar panels, they're connected in series and then series parallel from there, so that you get higher voltages coming from the panels. And what happens when the light hits the silicon material, the electrons in the outer valence ring are shifted into a higher state by photons coming from the sun. That's how they work. And I've got a system here at the house. I've got 32 panels sitting out in the back of the yard. They're connected in series parallel such that 300 volts DC comes into my house. And it comes into my inverter, which is one of these. It's a SolarArc 15K inverter. And it converts DC from the solar cells into AC for use in the house. It's also got a bunch of other functions. It's connected to batteries, so it'll keep the batteries charged. And it also works in parallel with Duke Energy, my electrical provider. So when I'm not using all my energy, I sell it back to Duke at a very minimal rate, but I provide power for my neighbors. So I think that's kind of cool. All right, moving on to a new topic. Anybody have an old radio with a dial cord, and you got to try to figure out how did this thing wrap around here such that when I turned a knob, that it actually turned this variable capacitor. This is probably what it looked like on the printed circuit board on the other side here. But this is a variable capacitor, a mechanical variable capacitor with stators, the stationary plates, and the rotors, the rotating plates. Well, in dial cord. Whew, boy, that was fun. But we don't typically tune radios that way anymore, at least amateur radio transceivers. We typically use a tuning voltage and a varactor diode circuit in oscillators to control them, or it may even be a digital analog converter that's used in this way. And the big knob is no longer connected to a dial cord, that big knob on your radio. It's probably using something called an optical shaft encoder system, where it it's got photocells, light source and photocells that read a pattern behind the big knob, and that is translated into a digital information that is used by the radio's computer to determine, are you tuning up? Are you tuning down? At what rate are you tuning? And it will act accordingly. So optical shaft encoders, also known as rotary encoders, it's a pattern that is read by optical sensors to allow you to tune your radio. No more dial cord. And another thing, those mechanical relays like I talked about before, well, this probably wouldn't work for transmit receive because I don't think they'll handle RF. But for power switching and things like that, solid state relays. They replace mechanical relays for switching functions, and one of these could be very handy, for example, if you've got an old amplifier that uses a high voltage push-to-talk sensing circuit. You might have to translate that to lower voltage for your modern transceiver. Solid-state relays can help in this regard. Okay, let's answer some questions and then we can take a break. So what absorbs the energy from light falling on a photovoltaic cell? The photons come in, and who gets the energy?
Charlie,
The electrons, because they're moved up to a higher energy level. And what happens to photoconductive material when light shines on it? Photoconductive material, when light shines on it,
alpha,
the resistance goes down. And what is the most common configuration of an optoisolator or optocoupler? Delta is correct. It's an LED and a phototransistor. And what is the photovoltaic effect?
bravo,
Bravo. The conversion of light to electrical energy. And which of the following describes an optical shaft decoder?
alpha,
You got it. A device that detects rotation by interrupting a light source with a patterned wheel. And which of these materials is most commonly used to create photoconductive devices?
Charlie,
We looked at all of that material. It's all crystalline semiconductor material. And what is a solid-state relay?
bravo,
Yeah, it's a device that uses semiconductors to implement the functions of an electromechanical relay. And why are optoisolators often used in conjunction with solid-state circuits that control 120 volt AC circuits?
Charlie,
Yeah, they're used in switching power supplies that provide an electrical isolation between the control circuit and the circuit being switched. And what is the efficiency of a photovoltaic cell?
delta,
Yeah, it's the relative fraction of light that is converted to current. I don't like this question, but okay. And what is the most common material used in power generating photovoltaic cells?
bravo,
Yep, silicon. And what is the approximate open circuit voltage produced by a fully illuminated single silicon photovoltaic cell?
Alpha.
Yep, 0.5 volts. And what is the purpose of an inverter connected to a solar panel output?
Delta.
Delta.
Like my Solarc, it converts the panel's output from DC to AC. Ladies and gentlemen, you've done great. You have earned your 5-minute intermission. Please get up and move around, stretch, and we'll be back to complete digital logic. Oh no, hang in there. And we are back. Thanks for coming back after your little stretch and trip down the hall, et cetera, et cetera. No details, please. But glad to have you here. We're going to talk about digital logic next. And it's interesting because back in the day, there was a lot more activity dealing with building digital circuits on your own. Control circuits, vending machine circuits, parking problems, things like that. I remember in classes that I took, we'd have to work through these logic problems and try to come up with circuits that would then allow us to come up with these functions. Well, we're going to talk about some of the changes that have been made. But the thing is, with amateur radio, if you've gone to Hamfests, you've seen that there's a lot of vintage equipment still being sold and used today. And a lot of the older radios or controllers, etc., are still out there. Our computers, a lot of them still have serial ports because we use serial ports to control radios and things like that. So digital logic has its place in amateur radio, and having some understanding about some of these things that we're going to talk about tonight is valuable. Although you may not do any troubleshooting, it's part of our tradition and history, and really a very important part of electronics. So let's go ahead and get started. Digital logic and digital electronics in 1 hour. Oh my goodness. All right. So what are we talking about when we're talking about digital? Well, on the left, there's in the time domain, we've got an analog signal which has a positive going voltage and a negative going voltage over time. And this is analog. It's continuous, and it could be any level that we have there on the screen. A digital signal is either a 1 or a 0. It's either high or it's low. And other than that, that's all it is. And so it's a reinterpretation of things into just a binary state. And George Boole was, I believe, a British mathematician back in 1847 who put together an entire algebra system based on these logical states. It's an algebra that deals with true or false, 1 and zeros, which later on became fundamental to digital electronics. And he came up with all sorts of axioms, which we don't need to know about. I'm just pointing these out to you. So one thing we do want to make sure that when we're talking about digital logic, are you positive? What we're talking about is there's something called positive logic, and there's also something called negative logic. Positive logic defines a high voltage as a 1. It is the most common type of logic. But back in the day when we were building these circuits with the digital chips and things, chips were expensive. Chips used a lot of power, especially TTL chips. And so we were looking for all sorts of ways to minimize the use of chips in circuits. And one way you can do that is by converting your thinking from positive logic to negative logic. Negative logic defines a low voltage as a 1. Well, what does that get you? Well, if you have a positive OR gate, it becomes a negative NAND gate. Or a positive AND gate becomes a negative OR gate. So this is just a little bit of history. You don't need to know other than positive logic, the most common kind of logic, defines high voltage as a 1. Keep that in mind. So the switch analogy for gates, this is what we would call an OR gate. It has 2 inputs, A and B. And you can maybe see the switches there. A just closed and open, B just closed and open. And both of them, I think, will close and open. Oh, they don't do both at the same time. But anyway, if one or the other, that's where the OR comes in, if one or the other closes or goes high, then our lamp will light. So this is the analogy for an OR gate. An AND gate, oops, what happened here? Come on, move ahead. There we go. AND gate if we put the switches in series with each other, what this means is that we have to have A closed and B closed, and when that happens, then we get an output, or the light lights up. So these are switch versions of gates, an OR gate and an AND gate. You can implement gates with switches, probably not the most logical way. You can implement gates with diodes. Diode logic is the most basic type, and sometimes this is a circuit that you might want to utilize. For example, if you've got one push-to-talk output on your radio, but you want to control two different amplifiers, and you don't want their voltages, the amplifier's voltages, to intermix with each other, well, sometimes you can rig up a circuit with diodes so that you can control the amplifier A and amplifier B independently using diodes. So diode logic is very basic. No matter what your family of logic you're going to use, so whether it's switches, diodes, etc., there's something called truth tables, and they're the same no matter what. So we have an AND gate truth table, a NAND gate truth table, an OR gate, a NOR gate, and a NOT gate. Well, let's take a look at the NOT gate. So here is a NOT gate, also known as an inverter. And you can tell it's an inverter by this little bubble on the output. That means it's negating. Whatever the input is, it'll give you the opposite. It's negating it. So when A is 1, it'll be 0 on the output. When A is 0, it'll be 1 on the output. And this is the truth table for this NOT gate, also known as an inverter. OR gate, all right, here's our truth table for an OR gate. A input, B input, and we can see it switching over here. A or B or both will give you a 1 on the output. This is an OR gate. An AND gate, here's the truth table. We have to have A and B be logic 1 in order to get logic 1 on the output. So these are all conditional things. These are, if this condition is true, then this condition is true, then we can act on it with an output. So that's what these circuits were all designed to do, is to implement some sort of logical function. Another kind of gate is an interesting one called the exclusive OR gate. It's an OR gate, and I determine OR, remember the letter O, it's rounded, so I see the letter O here, OR. Whereas AND gates are straight up and down, and the letter A has a straight up and down. So I know this is an AND gate, this is an OR gate, but it's got this line in front of it. That means it's exclusive. What that means is that A going to 1 will give me a 1, or B going to 1 will give me a 1, but if they both go to 1, I get a 0 on the output. And that's expressed in the truth table that we have over here. All right. Again, all of these gates and chips and whatnot were interconnected, and if you buy old equipment, and modems, etc., whatnot, you'll find these gates in there. AND gates, OR gates, buffer, not inverting, notice there's no circle on the output, exclusive OR, NAND gate, it's an AND gate with an inverter, a NOR gate, an OR gate with an inverter, a NOT gate, just an inverter, or here, an exclusive OR gate with an inverter is an XNOR gate. So I mentioned that different families of diode switching, diode transistor logic was one of the first chips that you could buy. They used a lot of power, and you couldn't interconnect them very well. So it got superseded by transistor logic, TTL. It had transistors on the input side, and a transistor, a single transistor, on the output side. TTL, very common, very popular. You can find it in amateur radio gear. The standard power supply voltage for TTL chips was 5 volts DC. The thing is that you had a target range. You wanted the low to be between 0 and 0.4 volts, and you wanted the high to be between 2.4 and 5 volts. in reality, you could go between 2 and 5 volts for a high, or up to 0.8 for a low. But this region in between is an uncertain region. Different chips would interpret it as a 1, and other chips would interpret it as a 0. So designers always had to make sure that they kept their chips at a voltage level that would be interpreted properly. And this troubleshooting digital logic, using logic analyzers and whatnot, you'd find certain things like this, that, oh, it's supposed to be a 1 there, but it's really a 0, or it's being interpreted as a 0. One thing you could do to positively control whether it would be a 0 or 1 when there was no signal is to put a pull-up or a pull-down resistor in the circuit. It's between a conductor and the positive power supply is a pull-up resistor, which means that anytime the switch was open, then you'd be sure that the input to this gate would be at 5 volts, so it would be interpreted as a 1. Whereas if the switch came in, it would short it to ground, it would go 0, and okay, it would interpret it as a 0. You can also have pull-down resistors to do the same thing, to try to avoid that uncertain region. They later improved for the TTL chips. Remember the early one I showed you there had just a single transistor on the output? Well, later they added transistors one on top of the other, one to pull it high and one to pull it low. This was called a totem pole configuration, and it allowed you to have increased numbers of chips after it, because it would be definitely pulled high or pulled low because of the totem pole output. And that more chips going out is called fan out, or more signals coming into the chip is called fan in. Just some terms of art there. So TTL was later replaced with CMOS, complementary metal oxide semiconductors. MOSFETs were used to implement the logic states. So CMOS uses much, much less power than TTL used to do. TTL circuits and boards and whatnot, you used to have massive high current power supplies in order to power all of the gates. Much smaller power supplies for CMOS. They still had a threshold, but they had greater noise margins because the switching threshold was typically about half of whatever the supply voltage was. There still was an uncertainty region, but it was much less than with TTL. So we had TTL, we have CMOS, and then we have something called bi-CMOS, which was a family of chips that used both. And you got the best of both worlds. You got CMOS chips on the input, and you got totem pole output here on the output for increased fan out. So best of both worlds is bi-CMOS. So with transistors or chips and things, you could actually put them together in specific configurations to do certain things. One configuration was called a flip-flop. It's a bistable circuit, meaning you could have it go in one state and it'll stay there, and then you can trigger it and it'll go in another state and stay there. That's bistable. It's got 2 stable states. So this was called a set-reset flip-flop. And you can kind of see the colors they're changing. When the set is indicated, the Q goes high. And when the reset is indicated, the Q goes low. So this is a set-reset flip-flop. Well, an engineer at Texas Instruments had an interesting idea. He said, what if we added another input so that the actions only took place when there was a clock pulse, a third pulse? And so they called this not a set-reset flip-flop, but a JK flip-flop in his name, in honor of his name, Jack Kilby. So this is a JK flip-flop. It is a set-reset flip-flop. Typically the K and J inputs may or may not be used, but the clock input is definitely used. And what happens with this is that every time the clock input comes in, it will alternate states. And what you can do with the JK flip-flop is that you can divide a digital signal frequency by 2. So for every 2 clock pulses that come in on the C input, only 1 is output on the Q output. And Q or not Q is Q was the positive logic, not Q is the negative logic or the inverse thereof. With JK flip-flops, you can do something called binary counting. If each divides the clock input by 2, if you run them in a chain, you can actually divide by 4, divide by 8, or with 4 chips, you can divide by 16. That's using the clock input on a JK flip-flop. Something to know about, and it doesn't have to use chips, you could use transistors, is what I call a digital oscillator, or it's a multi-vibrator. It is astable, meaning not stable at all. It's always alternating back and forth between different states at a known frequency, and you can adjust that frequency. And so you've got an output here, a Q output, or a not Q output, the inverse. And what's going on here is you're generating these digital pulses at a constant rate. So this can be used for timing circuits, this can be used for counting circuits. This is a multi-vibrator, astable multi-vibrator. And so you can see here with transistors, it's just outputting square wave signals on one side or the other. Now you can also have, this was an astable multi-vibrator. You can also have something called a monostable multi-vibrator. Why would you want to do that, Gary? Something we found with digital circuits that we never experienced with analog circuits. You know, push buttons, momentary contact switches. With analog circuits, you know, you push the button and the light lit up or the relay clicked or whatever, and you were good to go. Well, we didn't know that when you push that mechanical switch, as it was making contact, it was actually making contact, breaking contact, making contact, just minutely. And each one of those make and breaks, as you would push the switch contact together, would be counted by a digital circuit as a pulse. So you'd think you'd be pushing the button once, and you get 3 outputs. No, that's no good. Can't have that. So that's where the monostable multivibrator comes in. This is also called a debounce circuit, where you've got a switch, you push the button, and when you push that button, only one stable state occurs. It changes the output once and once only. Another version of a debouncing circuit is here. You've got the switch input here coming in on the trigger, and the output comes out here. And you can even adjust the output so that if you've got just a brief momentary push, it comes out at maybe a second long. So these are monostable multivibrators, known as debounce circuits. And another kind of multivibrator is the bistable type that has 2 stable states. It's a set-reset kind of multivibrator here using transistors. Another circuit that we use for counting is a chip called a decade counter. It's an integrated circuit that counts pulses and has 1 output for every 10 inputs. So you push the button over here, and you can see that it's counting the pulses up here, and here's number 10. It only lights every 10th time you push the button. Decade counters were important for frequency readouts and things like that we were using with normal numbers that humans interact with. The decade counters, you can buy them in chips. 4017B, for example, it has a clock input, reset and enable pulses, and then 10 output pins. Sometimes you'd only use one of the output pins. Another logic family that came into existence is something called tri-state. And it had nothing to do with New York, New Jersey, and Connecticut. No. Tri-state was this. You had a chip that had a high output state, or a low output state, or an open output state. It would actually disconnect itself from the circuit in this third variant. You use chip select lines, that's what the B is here, to actually enable the chip to be on the output line or to deselect it so it's not on the output line. So you could have something called a tri-state buffer, for example, so that if C was not authorized, if there's no 1 here, you'd have a high impedance state on the output. And then only when C was a number one state, a high state, could A, change the output from a 0 to a 1. Tri-state chips allowed more fan out. It allowed the ability to have more things going because you take the chips off. The more chips you have on a common connection called a bus, the more likely it is to either go high or to go low. But tri-state eliminated that. So just something to be aware of. It is a circuit that exists. All right, back in the day, and we were said, okay, we've got all these gates and whatnot, and we'd like to put them into an integrated circuit. Well, the manufacturers could do that, but what if I had a custom idea for a circuit that I wanted to put together? Well, you could have programmable logic devices. And some of the earliest programmable logic devices were such that you had a programmer and you'd systematically make circuits or blow fuses in circuits on this chip. And you would actually determine the functions that were going to go on this programmable logic device through this crude method. You can only do it once. And if you wanted to make a change, you had to pull the chip out, throw it away, get a new chip, reprogram it, and stick it back into the circuit. Well, nowadays, we've come a long way, baby. We have what are known as field programmable gate arrays. It's the same idea, except that it's a programmable logic device that can be reconfigured by software now. So you've got data input lines that can control this chip, and it's very, very complex logic. Back in the day, maybe you'd have 10 or 20 chips on board. This has got hundreds, if not thousands, of circuits on board that you can reconfigure. And you can program these FPGAs using something called hardware description language. The two most popular are VHDL and Verilog. So I have a flex radio, for example, my 6600, and every now and again they come out with new versions of Smart SDR software. And the Smart SDR software goes into the radio and reprograms the FPGAs inside the radio for the new functions that are being implemented. No more blowing fuses. Hallelujah. All right, let's answer some questions. So what is tri-state logic?
Charlie.
Not Charlie.
Alpha.
It is alpha, yeah. Logic devices with 0, 1, and a high impedance output state. And which of the following is an advantage of BiCMOS?
Charlie.
Charlie.
It's two transistor families in one. Yeah, it has the high input impedance of CMOS and the low output impedance of bipolar. And which of the following digital logic families has the lowest power consumption?
CMOS, delta.
Yep, CMOS.
Delta.
Indeed. And why do CMOS digital integrated circuits have high immunity to noise?
Charlie.
Charlie.
It is because the input switching threshold is about half of the power supply voltage. So anything that's noise is going to be likely less than that. And what best describes a pull up or pull down resistor?
Bravo.
It is. It's a resistor connected to the positive or negative supply used to establish a voltage when an input or output is an open circuit. You want to make sure it's not in that danger zone. All right. In this figure, which is the schematic symbol for a NAND gate?
Bravo.
So AND gates have straight lines on the front, and because it's NAND, it's inverting. So you see the straight line here, and NAND. So number 2, or B. Yep. And what is used to design the configuration of a field programmable gate array?
Oh, just did it.
Bravo.
Bravo.
Yeah, the hardware description language. And which is the schematic symbol for a NOR gate?
Delta.
Delta.
Yes, number 4, delta. And which is the schematic symbol for the NOT operation?
Charlie.
Charlie.
It's also known as an inverter, yeah, number 5. And which circuit is bistable? It has 2 stable states.
Charlie.
It can either be flipped or it can be flopped, a flip-flop. And what is the function of a decade counter?
Alpha.
Alpha.
Yeah, it produces 1 output pulse for every 10 input pulses. And which of the following can divide the frequency of a pulse train by 2?
Charlie.
Not Charlie.
Oh.
Delta.
Not delta.
Bravo.
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 It's a flip-flop, specifically the JK flip-flop. I wish they'd put that in there, but yeah, JK flip-flop can do it with the clock input. So how many flip-flops, JK flip-flops, are required to divide a signal frequency by 16?
Charlie.
Alpha.
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 It is alpha, 4. Divide by 2, divide by 4, divide by 8, divide by 16. So which of the following circuits continuously alternates between 2 states without an external clock signal?
Astable multivibrator. Delta.
Yeah, that is. It's astable, meaning it's oscillating. It's a digital oscillator. Yep. Astable multivibrator, D. And what is a characteristic of a monostable multivibrator?
Alpha.
This is the key, the switch debounce circuit. It switches temporarily to an alternate state for a set time. And what logical operation does a NAND gate perform?
These ones are gonna suck.
I know.
Delta.
Delta is correct. So if it was an AND gate, it would have an output of 1 if all inputs were 1. But because it's a NAND gate, it's a 0 at the output if all inputs are 1. That's a NAND gate. And what logical operation does an OR gate perform?
Alpha.
Alpha.
We see that? Yeah, it produces a 1 at its output if any input is 1. And what logical operation is performed by a 2-input exclusive NOR gate? Oh my God.
2 input exclusive.
You might have
Zeros.
to draw it out on paper and figure it out.
Delta.
Not delta.
Charlie.
It is Charlie. It produces a 0 at its output if 1 and only 1, that's the exclusive part, of its inputs is a 1.
I hate these.
Me too.
Well, and you don't have to deal with these much anymore, but for the test we need to know about them. So what is a truth table?
Bravo.
Yes, it's a list of inputs and corresponding outputs for a digital device. And what does positive logic mean?
Bravo.
High voltage represents 1, low voltage represents 0. And ladies and gentlemen, you made it. You made it to the end of chapter 5. I am so proud of you. Let me see if I can find the remove spotlight for our Zoom classroom. Are there any comments or questions you might have before we get out of here tonight?
Good class.
Nuts.
It was not an easy one, I know, but you're going for the extra class, so it's supposed to have some degree of difficulty. So, and there is a real history of this electronics being used in amateur radio. So it is worthwhile to have some familiarity with it. So would I have chosen these specific questions? Maybe not, but okay, we'll go with them. Dave, next week, what have we got next week?
All right, well, next week is going to be Chapter 6. Chapter 6 is radio, circuits, and systems. Gary has focused a lot on some of the individual components, and we're going to be putting those together to make functional blocks next week. Chapter 6 is pretty extensive. It's got 5 sections. We're going to only be talking about sections 1 and 2 for next week. So if you want to read ahead in the book, it's going to be sections 6.1, 6.2, that's through page 6-25. I will give you maybe some good news. They get into some very painful detail in the operation of common emitter and common base transistor circuits. You don't have to really understand all of that because you'll really get bogged down if you try to do so. We'll focus on the parts that you really need to know next week. We will touch on all of the important theory. So that's for next week, and the next 2 weeks you get to see me again.
Yay.
Yay!
So hang in there, y'all.
Hang in there, y'all.
You're doing it.
Yep.
It's
No,
coming. It's like learning a new language. It's very awkward at first.
And make sure you review between sessions. That's critical to getting through this.
Absolutely.
Yep.
All right.
Thank
Good.
you.
You bet.
Thank y'all.
Appreciate it.
We'll see you next week.
Thanks a lot.
73.
Appreciate it.
Thank you.
That was me.
Do you shut down the YouTube side?
So yeah, you can go 1, 2, 3 again and turn them off.
Or 3, 2, 1?
Yeah, 3, 2, 1, either one.